Iguanodon. Iguanodon/WNDN/ɪॻwɑːnədʒn, meaning iguana-tooth, named in 1825, is a genus of ornithopod dinosaur that existed roughly halfway between the first of the swift bipedal hypsilophodontids of the mid-Jurassic and the duck-billed dinosaurs of the late Cretaceous. While many species have been classified in the genus Iguanodon, dating from the late Jurassic period to the early Cretaceous period of Asia, Europe, and North America, taxonomic revision in the early 21st century has defined Iguanodon to be based on one well-substantiated species, Iburnis Artensis, which lived from the late Barremian to the earliest Aptian ages, early Cretaceous, in Belgium, Spain, Germany, England, Portugal and possibly elsewhere in Europe, between about 126 and 122 million years ago. Iguanodon were large, bulky herbivores. Distinctive features include large thumb spikes, which were possibly used for defense against predators, combined with long prehensile fifth fingers able to forage for food. The genus was named in 1825 by English geologist Gideon Mantell but discovered by William Harding Benstead, based on fossil specimens found in England, and was given the species name i-GWAH-nə-don. Iguanodon was the second type of dinosaur formally named based on fossil specimens, after Megalosaurus. Together with Megalosaurus and Hylaeosaurus, it was one of the three genera originally used to define Dinosauria. The genus Iguanodon belongs to the larger group Iguanodontia, along with the duck-billed hadrosaurs. The taxonomy of this genus continues to be a topic of study as new species are named or long-standing ones reassigned to other genera. In 1878 new, far more complete remains of Iguanodon were discovered in Belgium and studied by Louis Dallo. These were given the new species Iburnis Artensis. In the early 21st century it became understood that the remains referred to Iguanodon in England belonged to four different species, including Iburnis Artensis, that were not closely related to each other, which were subsequently split off into Mandylosaurus, Beryllium, and Hypsilophodontids. It was also found that the originally described type species of Iguanodon, i-GWAH-nə-don, was a nomen dubium, and not valid. Thus the name Iguanodon became fixed around the well-known species based primarily on the Belgian specimens. Scientific understanding of Iguanodon has evolved over time as new information has been obtained from fossils. The numerous specimens of this genus, including nearly complete skeletons from two well-known bone beds, have allowed researchers to make informed hypotheses regarding many aspects of the living animal, including feeding, movement, and social behavior. As one of the first scientifically well-known dinosaurs, Iguanodon has occupied a small but notable place in the public's perception of dinosaurs, its artistic representation changing significantly in response to new interpretations of its remains. Discovery and history. Gideon Mantell, Sir Richard Owen, and the discovery of dinosaurs. The discovery of Iguanodon has long been accompanied by a popular legend. The story goes that Gideon Mantell's wife, Marianne, discovered the first teeth of an iguanodon in the strata of Tilgate Forest in Whiteman's Green, Cookfield, Sussex, England, in 1822 while her husband was visiting a patient. However, there is no evidence that Mantell took his wife with him while seeing patients. Furthermore, he admitted in 1851 that he himself had found the teeth, although he had previously stated in 1827 that Mrs. Mantell had indeed found the first of the teeth later named Iguanodon. Other later authors agree that the story is not certainly false. It is known from his notebooks that Mantell first acquired large fossil bones from the quarry at Whiteman's Green in 1820. Because also theropod teeth were found, thus belonging to carnivores, he at first interpreted these bones, which he tried to combine into a partial skeleton, as those of a giant crocodile. In 1821 Mantell mentioned the find of herbivorous teeth and began to consider the possibility that a large herbivorous reptile was present in the strata. However, in his 1822 publication Fossils of the South Downs he as yet did not dare to suggest a connection between the teeth and his very incomplete skeleton, presuming that his finds presented two large forms, one carnivorous, an animal of the lizard tribe of enormous magnitude, the other herbivorous. In May 1822 he first presented the herbivorous teeth to the Royal Society of London, but the members, among them William Buckland, dismissed them as fish teeth or the incisors of a rhinoceros from a tertiary stratum. On June 23, 1823 Charles Lyell showed some to Georges Cuvier, during a soirée in Paris, but the famous French naturalist at once dismissed them as those of a rhinoceros. Though the very next day Cuvier retracted, Lyell reported only the dismissal to Mantell, who became rather diffident about the issue. In 1824 Buckland described Megalosaurus and was on that occasion invited to visit Mantell's collection. Seeing the bones on 6 March he agreed that these were of some giant saurian, though still denying it was a herbivore. Emboldened nevertheless, Mantell again sent some teeth to Cuvier, who answered on June 22, 1824 that he had determined that they were reptilian and quite possibly belonged to a giant herbivore. In a new edition that year of his Recherches sur les semence fossiles, Cuvier admitted his earlier mistake, leading to an immediate acceptance of Mantell and his new saurian in scientific circles. Mantell tried to corroborate his theory further by finding a modern-day parallel among extant reptiles. In September 1824 he visited the Royal College of Surgeons but at first failed to find comparable teeth. However, assistant curator Samuel Stutchbury recognized that they resembled those of an iguana he had recently prepared, albeit 20 times longer. In recognition of the resemblance of the teeth to those of the iguana, Mantell decided to name his new animal Iguanodon or iguana-tooth, from iguana and the Greek word delta nu, odon, odontos or tooth. Based on isometric scaling, he estimated that the creature might have been up to 18 meters, 59 feet, long, more than the 12-meter, 39 feet, length of Megalosaurus. His initial idea for a name was Iguanosaurus, iguana lizard, but his friend William Daniel Conover suggested that that name was more applicable to the iguana itself, so a better name would be iguanoids, iguana-like, or Iguanodon. He neglected to add a specific name to form a proper binomial, but one was supplied in 1829 by Friedrich Hall, i-Anglicum, which was later amended to i-Anglicus. Mantell sent a letter detailing his discovery to the local Portsmouth Philosophical Society in December 1824, several weeks after settling on a name for the fossil creature. The letter was read to members of the society at a meeting on 17th of December, and a report was published in the Hampshire Telegraph the following Monday 20th of December, which announced the name, misspelt as Iguanodon. Mantell formally published his findings on February 10, 1825, when he presented a paper on the remains to the Royal Society of London. A more complete specimen of a similar animal was discovered in a quarry in Maidstone, Kent, in 1834, Lower Greensand Formation, which Mantell soon acquired. He was led to identify it as an iguanodon based on its distinctive teeth. The Maidstone slab was utilized in the first skeletal reconstructions and artistic renderings of Iguanodon, but due to its incompleteness, Mantell made some mistakes, the most famous of which was the placement of what he thought was a horn on the nose. The discovery of much better specimens in later years revealed that the horn was actually a modified thumb. Still encased in rock, the Maidstone skeleton is currently displayed at the Natural History Museum in London. The Borough of Maidstone commemorated this find by adding an iguanodon as a supporter to their coat of arms in 1949. This specimen has become linked with the name I. mantelli, a species named in 1832 by Christian Eric Hermann von Meyer in place of I. anglicus, but it actually comes from a different formation than the original I. mantelli/I. anglicus material. The Maidstone specimen, also known as Gideon Mantell's mantelpiece, and formerly labeled McG 3741, was subsequently excluded from Iguanodon. It is classified as cf. Mantellisaurus by MacDonald, 2012, as cf. Mantellisaurus atherfieldensis by Norman, 2012, and made the holotype of a separate species Mantellodon carpenteri by Paul, 2012, but this is considered dubious and it is generally considered a specimen of Mantellisaurus. At the same time, tension began to build between Mantell and Richard Owen, an ambitious scientist with much better funding and society connections in the turbulent worlds of Reform Act-era British politics and science. Owen, a firm creationist, opposed the early versions of evolutionary science, transmutationism, then being debated, and used what he would soon coin as dinosaurs as a weapon in this conflict. With the paper describing Dinosauria, he scaled down dinosaurs from lengths of over 61 meters, 200 feet, determined that they were not simply giant lizards, and put forward that they were advanced and mammal-like, characteristics given to them by God. According to the understanding of the time, they could not have been transmuted from reptiles to mammal-like creatures. In 1849, a few years before his death in 1852, Mantell realized that iguanodonts were not heavy, pachyderm-like animals, as Owen was putting forward, but had slender forelimbs. However, his passing left him unable to participate in the creation of the Crystal Palace dinosaur sculptures, and so Owen's vision of the dinosaurs became that seen by the public for decades. With Benjamin Waterhouse Hawkins, he had nearly 24 life-size sculptures of various prehistoric animals built out of concrete sculpted over a steel and brick framework. 2 iguanodons, based on the Maidstone specimen, one standing and one resting on its belly, were included. Before the sculpture of the standing iguanodon was completed, he held a banquet for 20 inside it. Bernissartensis discoveries and Ola's new reconstruction. The largest find of Iguanodon remains to that date occurred on February 28, 1878 in a coal mine at Bernissartensis in Belgium, at a depth of 322 meters, 1,056 feet, when two mine workers, Jules Creter and Alphonse Blanchard, accidentally hit on a skeleton that they initially took for petrified wood. With the encouragement of Alphonse Briard, supervisor of mines at nearby Moorland Wells, Louis de Pauw on May 15, 1878 started to excavate the skeletons, and in 1882 Louis Dallo reconstructed them. At least 38 Iguanodon individuals were uncovered, most of which were adults. In 1882, the holotype specimen of Iburnis Artensis became one of the first ever dinosaur skeletons mounted for display. It was put together in a chapel at the Palace of Charles of Lorraine using a series of adjustable ropes attached to scaffolding so that a lifelike pose could be achieved during the mounting process. This specimen, along with several others, first opened for public viewing in an inner courtyard of the palace in July 1883. In 1891 they were moved to the Royal Museum of Natural History, where they are still on display. 9 are displayed as standing mounts, and 19 more are still in the museum's basement. The exhibit makes an impressive display in the Royal Belgian Institute of Natural Sciences, in Brussels. A replica of one of these is on display at the Oxford University Museum of Natural History and at the Sedgwick Museum in Cambridge. Most of the remains were referred to a new species, Iburnis Artensis, a larger and much more robust animal than the English remains had yet revealed. One specimen, Ursund 1551, was at first referred to the nebulous, gracile Mantelli, but is currently referred to Mantellosaurus atherfieldensis. The skeletons were some of the first complete dinosaur skeletons known. Found with the dinosaur skeletons were the remains of plants, fish, and other reptiles, including the crocodiliform bernissartensis. The science of conserving fossil remains was in its infancy, and new techniques had to be improvised to deal with what soon became known as Pyrite Disease. Crystalline pyrite in the bones was being oxidized to iron sulfate, accompanied by an increase in volume that caused the remains to crack and crumble. When in the ground, the bones were isolated by anoxic moist clay that prevented this from happening, but when removed into the drier open air, the natural chemical conversion began to occur. To limit this effect, de Pauw immediately, in the mine gallery, recovered the dug-out fossils with wet clay, sealing them with paper and plaster reinforced by iron rings, forming in total about 600 transportable blocks with a combined weight of 130 tons. In Brussels, after opening the plaster, he impregnated the bones with boiling gelatin mixed with oil of cloves as a preservative. Removing most of the visible pyrite, he then hardened them with hide glue, finishing with a final layer of tin foil. Damage was repaired with paper mache. This treatment had the unintended effect of sealing in moisture and extending the period of damage. In 1932, museum director Victor van Strelen decided that the specimens had to be completely restored again to safeguard their preservation. From December 1935 to August 1936, the staff at the museum in Brussels treated the problem with a combination of alcohol, arsenic, and 390 kilograms of shellac. This combination was intended to simultaneously penetrate the fossils, with alcohol, prevent the development of mold, with arsenic, and harden them, with shellac. The fossils entered a third round of conservation from 2003 until May 2007, when the shellac, hide glue and gelatin were removed and impregnated with polyvinyl acetate and cyanoacrylate and epoxy glues. Modern treatments of this problem typically involve either monitoring the humidity of fossil storage, or, for fresh specimens, preparing a special coating of polyethylene glycol that is then heated in a vacuum pump, so that moisture is immediately removed and pore spaces are infiltrated with polyethylene glycol to seal and strengthen the fossil. Dallo's specimens allowed him to show that Owen's prehistoric pachyderms were not correct for Iguanodon. He instead modeled the skeletal mounts after the cassowarian wallaby, and put the spike that had been on the nose firmly on the thumb. His reconstruction would prevail for a long period of time, but would later be discounted. Excavations at the quarry were stopped in 1881, although it was not exhausted of fossils, as recent drilling operations have shown. During World War I, when the town was occupied by German forces, preparations were made to reopen the mine for paleontology, and Otto Jekyll was sent from Berlin to supervise. Just as the first fossiliferous layer was about to be uncovered, however, the German army surrendered and had to withdraw. Further attempts to reopen the mine were hindered by financial problems and were stopped altogether in 1921 when the mine flooded. Turn of the century and the dinosaur renaissance. Research on Iguanodon decreased during the early part of the 20th century as world wars and the Great Depression enveloped Europe. A new species that would become the subject of much study and taxonomic controversy, I-atherfieldensis, was named in 1925 by R. W. Hooley, for a specimen collected at Atherfield Point on the Isle of Wight. Iguanodon was not part of the initial work of the dinosaur renaissance that began with the description of Deinonychus in 1969, but it was not neglected for long. David B. Weishampel's work on ornithopod feeding mechanisms provided a better understanding of how it fed, and David B. Norman's work on numerous aspects of the genus has made it one of the best-known dinosaurs. In addition, a further find of numerous disarticulated iguanodon bones in Nieden, Nordrhein-Westfalen, Germany, has provided evidence for gregariousness in this genus, as the animals in this areally restricted find appear to have been killed by flash floods. At least 15 individuals, from 2 to 8 meters, 6 feet 7 into 26 feet 3 in, long, have been found here. Most of the individuals belong to the related Mandylosaurus, described as Iburnis, at that time believed to be another species of Iguanodon. But some are of Iburnis Artensis. One major revision to Iguanodon brought by the Renaissance would be another rethinking of how to reconstruct the animal. A major flaw with Dalla's reconstruction was the bend he introduced into the tail. This organ was more or less straight, as shown by the skeletons he was excavating, and the presence of ossified tendons. In fact, to get the bend in the tail for a more wallaby or kangaroo-like posture, the tail would have had to be broken. With its correct, straight tail and back, the animal would have walked with its body held horizontal to the ground, arms in place to support the body if needed. 21st century research and the splitting of the genus. In the 21st century, Iguanodon material has been used in the search for dinosaur biomolecules. In research by Graham Embry et al., Iguanodon bones were processed to look for remnant proteins. In this research, identifiable remains of typical bone proteins, such as phosphoproteins and proteoglycans, were found in a rib. In 2007, Gregory S. Paul split Iburnis into a new, separate genus, Mandylosaurus, which has been generally accepted. In 2009, fragmentary iguanodontid material was described from upper Barremian Paris Basin deposits in Auxerre, Burgundy. While not definitively diagnosable to the genus/species level, the specimen shares obvious morphological and dimensional affinities with Iburnis Artensis. In 2010, David Norman split the Phalanginian species I.Dawsoni and I-Phytoni into Beryllium and Hypsilophodontids respectively. After Norman 2010, over half a dozen new genera were named off English Iguanodon material. Carpenter and Ishida in 2010 named Proplanocoxa, Pterillion and Selicoxa, while Gregory S. Paul in 2012 named Darwinsaurus, Huxleysaurus and Mandylosaurus, and McDonald et al. In 2012 named Cucufeldia. These species named after Norman 2010 are not considered valid and are considered various junior synonyms of Mandylosaurus, Beryllium, and Hypsilophodontids. In 2011, a new genus Delaparendia was named for a specimen in Spain that was originally thought to belong to Iburnis Artensis. The previous identification was subsequently reaffirmed in a new analysis of individual variation in the Belgian specimens, finding that the Delaparendia specimen was within the range of Iburnis Artensis. In 2015, a new species of Iguanodon, Agalvensis, was named based on material including 13 juvenile, perinate, individuals found in the Camarillas Formation near Galve, Spain. In 2017, a new study was done of Agalvensis, with further evidence of distinctiveness from Iburnis Artensis, including several new autapomorphies. It was also found that the Delaparendia holotype, which is also from the Camarillas Formation, was not distinguishable from either Iburnis Artensis or Agalvensis. Description: Iguanodon were bulky herbivores that could shift from bipedality to quadrupedality. The only well-supported species, Iburnis Artensis, is estimated to have weighed about 3.08 tons, 3.4 tons, on average, and measured about 10 meters, 33 feet, long as an adult, with some specimens possibly as long as 13 meters, 43 feet. These animals had large, tall but narrow skulls, with toothless beaks probably covered with keratin, and teeth like those of iguanas, but much larger and more closely packed. The arms of Iburnis Artensis were long, up to 75% the length of the legs, and robust, with rather inflexible hands built so that the 3 central fingers could bear weight. The thumbs were conical spikes that stuck out away from the 3 main digits. In early restorations, the spike was placed on the animal's nose. Later fossils revealed the true nature of the thumb spikes, although their exact function is still debated. They could have been used for defense, or for foraging for food. The little finger was elongated and dexterous, and could have been used to manipulate objects. The phalangeal formula is 2-3-3-2-4, meaning that the innermost finger, phalange, has 2 bones, the next has 3, etc. The legs were powerful, but not built for running, and each foot had 3 toes. The backbone and tail were supported and stiffened by ossified tendons, which were tendons that turned to bone during life. These rod-like bones are usually omitted from skeletal mounts and drawings. Iguanodon teeth are, as the name suggests, like those of an iguana, but larger. Unlike hadrosaurids, which had columns of replacement teeth, Iguanodon only had one replacement tooth at a time for each position. The upper jaw held up to 29 teeth per side, with none at the front of the jaw, and the lower jaw 25. The numbers differ because teeth in the lower jaw are broader than those in the upper. Because the tooth rows are deeply inset from the outside of the jaws, and because of other anatomical details, it is believed that, as with most other ornithischians, Iguanodon had some sort of cheek-like structure, muscular or non-muscular, to retain food in the mouth. Classification and evolution. Iguanodon gives its name to the unranked clade Iguanodontia, a very populous group of ornithopods with many species known from the Middle Jurassic to the Late Cretaceous. Aside from Iguanodon, the best-known members of the clade include Dryosaurus, Camptosaurus, Auranosaurus, and the duckbills, or hadrosaurs. In older sources, Iguanodontidae was shown as a distinct family. This family traditionally has been something of a wastebasket taxon, including ornithopods that were neither hypsilophodontids or hadrosaurids. In practice, animals like Colovosaurus, Camptosaurus, Craspetodon, Cagnosaurus, Mauchlodon, Muttaburrasaurus, Auranosaurus, and Probactrosaurus were usually assigned to this family. With the advent of cladistic analyses, Iguanodontidae was traditionally construed was shown to be paraphyletic, and these animals are recognized to fall at different points in relation to hadrosaurs on a cladogram, instead of in a single distinct clade. Essentially, the modern concept of Iguanodontidae currently includes only Iguanodon. Groups like Iguanodontoidea are still used as unranked clades in the scientific literature, though many traditional iguanodontids are now included in the superfamily Hadrosauroidea. Iguanodon lies between Camptosaurus and Auranosaurus in cladograms, and is probably descended from a camptosaur-like animal. At one point, Jack Horner suggested, based mostly on skull features, that hadrosaurids actually form two more distantly related groups, with Iguanodon on the line to the flat-headed hadrosaurines, and Auranosaurus on the line to the crested lamiosaurines, but his proposal has been rejected. The cladogram below follows an analysis by Andrew MacDonald, 2012. Species. Because Iguanodon is one of the first dinosaur genera to have been named, numerous species have been assigned to it. While never becoming the wastebasket taxon, several other early genera of dinosaurs, such as Megalosaurus, became. Iguanodon has had a complicated history, and its taxonomy continues to undergo revisions. Although Gregory Paul recommended restricting Iburnis Artensis to the famous sample from Bernissart, ornithopod workers like Norman and MacDonald have disagreed with Paul's recommendations, except exercising caution when accepting records of Iguanodon from France and Spain as valid. i-GWAH-nə-don was the original type species, but the lectotype was based on a single tooth and only partial remains of the species have been recovered since. In March 2000, the International Commission on Zoological Nomenclature changed the type species to the much better known Iburnis Artensis, with the new holotype being IRSN 1534. The original Iguanodon tooth is held at Te Papatongarewa, the National Museum of New Zealand in Wellington, although it is not on display. The fossil arrived in New Zealand following the move of Gideon Mantell's son Walter there. After the elder Mantell's death, his fossils went to Walter. Species currently accepted as valid. Only 2 species assigned to Iguanodon are still considered to be valid. Reassigned species of Iguanodon. Species reassigned to Iguanodon. Dubious species. Paleobiology Feeding. One of the first details noted about Iguanodon was that it had the teeth of a herbivorous reptile, although there has not always been consensus on how it ate. As Mantell noted, the remains he was working with were unlike any modern reptile, especially in the toothless, scoop-shaped form of the lower jaw symphysis, which he found best compared to that of the two-toed sloth and the extinct ground sloth Mylodon. He also suggested that Iguanodon had a prehensile tongue which could be used to gather food, like a giraffe. More complete remains have shown this to be an error. For example, the hyoid bones that supported the tongue are heavily built, implying a muscular, non-prehensile tongue used for moving food around in the mouth. The giraffe tongue idea has also been incorrectly attributed to Dalla via broken lower jaw. The skull was structured in such a way that as it closed, the bones holding the teeth in the upper jaw would bow out. This would cause the lower surfaces of the upper jaw teeth to rub against the upper surface of the lower jaw's teeth, grinding anything caught in between and providing an action that is the rough equivalent of mammalian chewing. Because the teeth were always replaced, The animal could have used this mechanism throughout its life, and could eat tough plant material. Additionally, the front ends of the animal's jaws were toothless and tipped with bony nodes, both upper and lower, providing a rough margin that was likely covered and lengthened by a keratinous material to form a cropping beak for biting off twigs and shoots. Its food gathering would have been aided by its flexible little finger, which could have been used to manipulate objects, unlike the other fingers. Exactly what Iguanodon ate with its well-developed jaws is not known. The size of the larger species, such as Iburnis Artensis, would have allowed them access to food from ground level to tree foliage at 4 to 5 meters, 13 to 16 feet, high. A diet of horsetails, cycads, and conifers was suggested by David Norman, although iguanodonts in general have been tied to the advance of angiosperm plants in the Cretaceous due to the dinosaurs' inferred low browsing habits. Angiosperm growth, according to this hypothesis, would have been encouraged by iguanodon feeding because gymnosperms would be removed, allowing more space for the weed-like early angiosperms to grow. The evidence is not conclusive, though. Whatever its exact diet, due to its size and abundance, Iguanodon is regarded as a dominant medium to large herbivore for its ecological communities. In England, this included the small predator Aristosuchus, larger predators Eodoranus, Baryonyx, and Neovenator, low-feeding herbivores Hypsilophodon and Baldosaurus, fellow iguanodontid Mandylosaurus, the armored herbivore Polacanthus, and sauropods like Pelorosaurus. Posture and movement. Early fossil remains were fragmentary, which led to much speculation on the posture and nature of Iguanodon. Iguanodon was initially portrayed as a quadrupedal horn-nosed beast. However, as more bones were discovered, Mantell observed that the forelimbs were much smaller than the hindlimbs. His rival Owen was of the opinion it was a stumpy creature with 4 pillar-like legs. The job of overseeing the first life-size reconstruction of dinosaurs was initially offered to Mantell, who declined due to poor health, and Owen's vision subsequently formed the basis on which the sculptures took shape. Its bipedal nature was revealed with the discovery of the bernissart skeletons. However, it was depicted in an upright posture, with the tail dragging along the ground, acting as the third leg of a tripod. During his re-examination of Iguanodon, David Norman was able to show that this posture was unlikely, because the long tail was stiffened with ossified tendons. To get the tripodal pose, the tail would literally have to be broken. Putting the animal in a horizontal posture makes many aspects of the arms and pectoral girdle more understandable. For example, the hand is relatively immobile, with the 3 central fingers grouped together, bearing hoof-like phalanges, and able to hyperextend. This would have allowed them to bear weight. The wrist is also relatively immobile, and the arms and shoulder bones robust. These features all suggest that the animal spent time on all fours. Furthermore, it appears that Iguanodon became more quadrupedal as it got older and heavier. Juvenile Iburnis Artensis have shorter arms than adults, 60% of hindlimb length versus 70% for adults. When walking as a quadruped, the animal's hands would have been held so that the palms faced each other, as shown by iguanodontian trackways and the anatomy of this genus's arms and hands. The 3-toed pes, foot, of Iguanodon was relatively long, and when walking, both the hand and the foot would have been used in a digitigrade fashion, walking on the fingers and toes. The maximum speed of Iguanodon has been estimated at 24 km per hour, 15 miles per hour, which would have been as a biped. It would not have been able to gallop as a quadruped. Large 3-toed footprints are known in early Cretaceous rocks of England, particularly Wealden beds on the Isle of Wight, and these trace fossils were originally difficult to interpret. Some authors associated them with dinosaurs early on. In 1846, E. Taggart went so far as to assign them to an ichnogenus he named Iguanodon, and Samuel Beckles noted in 1854 that they looked like bird tracks, but might have come from dinosaurs. The identity of the track makers was greatly clarified upon the discovery in 1857 of the hind leg of a young iguanodon, with distinctly 3-toed feet, showing that such dinosaurs could have made the tracks. Despite the lack of direct evidence, these tracks are often attributed to Iguanodon. A trackway in England shows what may be an iguanodon moving on all fours, but the footprints are poor, making a direct connection difficult. Tracks assigned to the ichnogenus Iguanodon are known from locations including places in Europe where the body fossil Iguanodon is known, to Spitsbergen, Svalbard, Norway. Thumb spike. The thumb spike is one of the best-known features of Iguanodon. Although it was originally placed on the animal's nose by Mantell, the complete bernissart specimens allowed Dallo to place it correctly on the hand, as a modified thumb. This would not be the last time a dinosaur's modified thumb claw would be misinterpreted. Noasaurus, Baryonyx, and Megaraptor are examples since the 1980s where an enlarged thumb claw was first put on the foot, as in dromaeosaurids. This thumb is typically interpreted as a close-quarter stiletto-like weapon against predators, although it could also have been used to break into seeds and fruits, or against other Iguanodon. One author has suggested that the spike was attached to a venom gland, but this has not been accepted, as the spike was not hollow, nor were there any grooves on the spike for conducting venom. Possible social behavior. Although sometimes interpreted as the result of a single catastrophe, the Bernissart finds instead are now interpreted as recording multiple events. According to this interpretation, at least 3 occasions of mortality are recorded, and though numerous individuals would have died in a geologically short time span, (10 to 100 years), this does not necessarily mean these Iguanodon were herding animals. An argument against herding is that juvenile remains are very uncommon at this site, unlike modern cases with herd mortality. They more likely were the periodic victims of flash floods whose carcasses accumulated in a lake or marshy setting. The Neaton find, however, with its greater span of individual ages, more even mix of Dolodon or Mantellosaurus to Iguanodon Bernissartensis, and confined geographic nature, may record mortality of herding animals migrating through rivers. There is no evidence that Iguanodon was sexually dimorphic, with one sex appreciably different from the other. At one time, it was suggested that the Bernissart I-Mantelli, or Iatharfieldinsis, Dolodon and Mantellosaurus, respectively, represented a sex, possibly female, of the larger and more robust, possibly male, Iburnis Artensis. However, this is not supported today. A 2017 analysis showed that Iburnis Artensis does exhibit a large level of individual variation in both its limbs, scapula, humerus, thumb claw, ilium, ischium, femur, tibia, and spinal column, axis, sacrum, tail vertebrae. Additionally, this analysis found that individuals of Iburnis Artensis generally seem to fall into 2 categories based on whether their tail vertebrae bore a furrow on the bottom, and whether their thumb claws were large or small. Paleopathology. Evidence of a fractured hip bone was found in a specimen of Iguanodon, which had an injury to its ischium. 2 other individuals were observed with signs of osteoarthritis as evidenced by bone overgrowths in their ankle bones which are called osteophytes. In popular culture. Since its description in 1825, Iguanodon has been a feature of worldwide popular culture. 2 life-size reconstructions of Mantelodon, considered Iguanodon at the time, built at the Crystal Palace in London in 1852 greatly contributed to the popularity of the genus. Their thumb spikes were mistaken for horns, and they were depicted as elephant-like quadrupeds, yet this was the first time an attempt was made at constructing full-size dinosaur models. In 1910 Heinrich Harter portrayed a group of Iguanodon in the classic German collecting cards about extinct and prehistoric animals Tiere der Urwelt. Several motion pictures have featured Iguanodon. In the 2000 Disney animated film Dinosaur, an Iguanodon named Alidar served as the protagonist with 4 other Iguanodons as other main characters are Nera, Kron, Bruten and his unnamed scout. A loosely related ride of the same name at Disney's Animal Kingdom is based around bringing an Iguanodon back to the present. Iguanodon is one of the 3 dinosaur genera that inspired Godzilla, the other 2 were Tyrannosaurus rex and Stegosaurus. Iguanodon has also made appearances in some of the many The Land Before Time films, as well as episodes of the television series. Aside from appearances in movies, Iguanodon has also been featured on the television documentary miniseries Walking with Dinosaurs, 1999, produced by the BBC, along with an undescribed Iguanodon lakotaensis, and played a starring role in Sir Arthur Conan Doyle's book, The Lost World, as well as featuring in the 2015 documentary Dinosaur Britain. It also was present in Bob Backer's Raptor Red, 1995, as a Utahraptor prey item. A main belt asteroid, 1989 CB3, has been named 9941 Iguanodon in honor of the genus. Because it is both one of the first dinosaurs described and one of the best-known dinosaurs, Iguanodon has been well placed as a barometer of changing public and scientific perceptions on dinosaurs. Its reconstructions have gone through 3 stages. The elephantine quadrupedal horn-snouted reptile satisfied the Victorians, then a bipedal but still fundamentally reptilian animal using its tail to prop itself up dominated the early 20th century, but was slowly overturned during the 1960s by its current, more agile and dynamic representation, able to shift from 2 legs to all 4s.